Welcome, YouTubers. Another day of physics with me, your host, Zio. Today, we're going to try something a little bit different. The forum is going to be a little bit different. I've invited a special guest to the forum to ask some questions about some of the things we're talking about. It'd be nice to be able to communicate with all of you. Maybe one day I'll put up some screens and I can do like a live chat or a stream. And that way I can really dig deeper into what's going on these boards. Because it appears that I can't ask as many questions as I can answer. But that's all right. We'll still get around to a lot of the answers that we've been seeking throughout our journey in science. So on the board behind me, you'll notice I have some things you might recognize. For example, this big thing on the right here, or my right, is what I'm currently constructing in my own theories as the structure of a black hole and some of the processes that it goes through in converting normal matter into subspatial matter, or subspatial dark iron in this particular case. I had to really kind of understand what was going on there. You know, in the beginning I thought too small. I'm thinking like planets. Well, planets are a part of it, but it appears that star cores, as you've seen from my other videos, in the center of all active stars there's a ringing top of sorts made of iron that's, well, you probably should watch the other videos, but for now let's go ahead and get into some of the stuff that I've got on the board behind me. Just understand, what I'll be talking about is based upon the previous videos. If you haven't watched those yet, you might want to go back and watch them so you can kind of catch up and get to where we are today. Alright, so on the board, as I'm looking here, let's go ahead and look at some of the things we have. This is, like I said, my diagram of a black hole and some of the forces and structures found within. Some of the most recent things discovered by NASA with their observations of black holes has been how the matter gets pulled apart before it's sucked into a black hole. And you know, this is the same thing that I'm talking about here. These lines, of course, represent lines of force, where space has been bent to an infinite point. You know, it starts out kind of flat, and then it gets curved, more curved, till it's almost a sharp point. And that's where normal space is pulled in to a point of highest mass. And you know, that process in itself, if you talked about how we ended up with a black hole are kind of mysterious, but this particular one that I'm referring to is a galactic black hole. So aside from the normal stellar or star-based black holes, this one's made up of millions of masses of stars. You know, it's 2.4 million mass, stellar mass core, I believe. And that in of itself kind of lends to what we're seeing now. Instead of seeing a top, or an iron top looking thing like we see inside a star, what we're seeing instead is a ring. And the ring itself is not a solid ring. It's made up of basically giant cables of material, and in this case that material is dark matter that has been continually injected into the surrounding space. It's essentially an orbit of the black hole. You end up with a belt, kind of like our Van Allen radiation belt. You got charged particles, or in this case anything that would be an orbit of a point of highest mass. The point of highest mass is essentially a virtual point in this layer of reality. There isn't a something in the middle so much as there is a bunch of somethings across many dimensions. And that creates a near infinite focal point, or a near point of highest mass, near infinite point of highest mass in our space, essentially creating a origin point for XYZ in a galaxy. Now, in this case right here, we're just going to go through the mechanics of it real quick, just see what happens. We have a star, and if you look into some of our more recent observations of the core of the Milky Way, where the giant black hole is, or they say there's a couple of, but the big one is what I'm talking about. You'll see that it pulls in a star every once in a while. And when that star is pulled in, of course, we got to think about some of the processes. Well, inside that star, it has a iron core. Okay, the iron core is pulled in, and you end up with this cavity effect right here. This cavity effect is the crushing, oscillating, shearing forces along the equatorial plane in the very center here. So your point of highest mass is right there in the center. And this crushes, it stretches the iron and crushes it down into a noodle of sorts. And the fingers, it's not stable. It's not like perfectly cylindrical. They kind of do like this, like little fingers, those little opening and closings. And then, of course, you have a threshold that is met where, as I talked about in my superfusion video, where your compression exceeds, or I guess a better way to put it would be to take normal material and crush it down so far that it enters the next, or the underverse layer or subspatial layer of transverse binding energy, which exists at a higher frequency than what we have up here. So once it reaches that transverse binding point, it can now sustain its three-dimensional existence at that layer. And so essentially it takes the iron, squeezes it down into a little noodle, and then the noodle essentially flies apart. The iron just goes, just spreads out, and that of course is thrown out in radial bands out to the awaiting ring, which is in orbit of that point of highest mass. Now in this ring you're going to have belts, kind of like well, like in a tire, steel belted radio. Well, it's essentially what you've got here. You got dark iron belted black hole. That's what you have, and that dark iron, of course, is in orbit of that point of highest mass. And along the equatorial plane of the galaxy, you have the mass of the galaxy being aligned to that point. There's a radial attraction of matter. This is essentially creates a dark matter ring, as you can see here, a dark matter ring. And of course, this is also the black hole event horizon, where light can't escape, or well, we're not seeing as much light from that point. So this gravity attracts dark matter towards the core, offset by the rate of spin. So the rate of spin of your black hole means that the matter itself cannot enter the physical zone right here. This large belt of matter wouldn't really fall down into that core because it's in orbit of it, and that orbit is dictated by the amount of matter out in the outer ring, or the outer arms of the galaxy. And those two factors maintain Newton's law of attraction, and you end up with, well, an orbiting band. Now that of course ends up being a sponge for dark matter and dark energies that pass through that area. Some of the things to talk about, other than the compression snippy core here that takes iron and crushes it down. The reason why you're ending up with dark iron, and so much of it, I was having some trouble understanding why so much dark matter. See, I was under the understanding that the core of a sun or the core of a planet is basically being crushed like a jawbreaker down into a point to where the flux lines from that entire mass create an overlapping flux line pattern that exceeds the shearing forces of the black hole, which is near infinity. That could be something that happens, but more likely it's that it has this systematic conveyor belt or assembly line system here, where it either pinches off very discrete amounts of the matter, or basically fire hose sprays the iron into subspace, and that could happen from either side of the black hole. Now, of course, the spray that we're seeing from the core of a galaxy appears to be gamma, so maybe gamma is kind of like a waste product in the reaction. Gamma, as you know, can pass through normal matter, so the gamma that is generated probably from Z particles inside this reaction, that's positrons and electrons, that's called a positronium. A positronium decays into a Z particle, and then the Z particle decays into gamma particles, so gamma photons. And the gamma photon, as soon as it reaches gamma levels, it can pass freely through most matter. And it would be one of the few things that could escape a black hole would be gamma. And in this case, we have two very large jets that emit from a galactic core black hole. And that's this right here, the gamma comes out. Okay, so let's talk about what I was mentioning a second ago. How I saw so much of this this dark iron down in the subspatial layer as I'm examining and researching these effects, and I'm like, well, how can there be so much of it, and why is it all the same size, and why is there just so much of it? Because we got to have all this, you know, if dark iron truly is the material for monopolaric electrons, you know, kind of like north and south. Well, that's essentially what we're seeing there. But these things are tiny. They're really, really, really small. And to get so much of them down there, you need a whole bunch of it just getting shoved there all the time, everywhere throughout the universe, throughout all time. So, and I was like looking at electrons. Well, there's a whole bunch of them. I mean, it makes sense why they have a charge. It makes sense because if those are now, this isn't one piece of dark iron. That's another thing too. Somebody asked me. They're like, so you're saying that's one dark atom of dark iron? I'm like, no. That's these are thousands or millions or even billions or trillions of individual teeny tiny pieces that are locked into a subspatial layer of transverse binding energy, which sustains their three-dimensional structure on that layer. They weakly interact with our layer as electrons, or what we see as electrons. So the fractal compression from that layer, as I stated before, it appears that electrons, based upon their dark iron makeup, they look just like a universe, strangely enough. What we see on our large macro scale or mega scale as our universe, the distribution of matter and how it falls into strands and bands and trees and rivers and all those other things that you see when we image our universe with our various imaging devices looks very similar to what I'm seeing electrons and all their little stacks of stuff inside there. So, you know, that's very interesting, of course, in the dark iron. But today, like I said, we have a special guest, and the special guest is going to ask some questions about what is on the board here. We're hopefully going to stay on topic and pretty much focus on those things that pertain to these things. So I'd like to now introduce him. You know, this is my son, Chris, and he'll be speaking in the background. You'll hear his voice, and perhaps in future videos, of course, or maybe even this one, you get to meet him and see him. So what's your first question for what's on the board behind us today, Chris?
Well, it's given that the electron isn't a purely negative charge. I think you said earlier that it works like magnets.
Yeah, it does. Interestingly enough, if you have enough of this material, and remember you have a spin as well. So if you took like a clump of little tiny powerful magnets and you spun them in free space, well, all those little magnets technically could align to where all the poles are facing outwards in a perfectly balanced spun environment where you have all these little magnets that are approximately the same shape and super strength. So essentially, even though electrons on the outside appear to have a negative charge, let's just call negative north for now. I mean, just like a generator, we have positive and negative depending on which pole you're talking about.
Well, my question is, how does the form stabilize?
Spin.
When do the plus aligned sides repel each other?
You know, that's the other thing too. It's that's a reaction between the massiveness of the particles.
Okay.
So the point of highest mass. So somewhere in the middle of an electron, there is a single electron or a group of them. If you've ever seen how those things work.
That's attracting them all and overcoming.
Yeah, it's essentially you have a clumpy core.
Okay.
And that clumpy core, in this case, everything is bound to a single particle in the middle. So are you saying in the very center of this, is there a positive particle? Imagine it more like
what is a neutral particle?
No, neutral is different. Neutral is a combination. I can explain that in a minute. Imagine you have this this alignment. It's almost like super alignment where you have all these lines that come inward, and all the magnets are basically stacked up perfectly towards the core, like that. And in the very center, now admittedly you say, won't they all repel off each other? Yes, they will, creating a cavity. So in the center of an electron, there's a cavity that has nothing, a void. So that is true. Is that your question?
Well, my second question is, yeah, that was my question.
Okay,
my second question is, so iron as we know it is a certain combination of electrons, protons, neutrons.
Yes.
You need 50 grams to make a mole of iron.
50 grams?
50 something grams to make a mole of iron.
Okay.
Can't recall the exact number. So, electrons are also made of in a compressed state of iron.
Yeah, electrons, it appears that they are a compressed state of iron, dark iron, that's been pushed down via black hole or supernova into a subspace transverse binding point where the energies that transverse that material are aligned to essentially sustain it on that layer of existence.
Alright. What about protons and neutrons?
What about them?
Are they made of iron too?
Well, you know, that's interesting. When I looked at protons and neutrons, they, you know, if you look at the up quark network, I have another video on that, and what I explained in that was you have two up quarks and a down quark. Two up positive 2/3 quarks and one down negative 1/3 quark, which is twice the mass of the two up quarks. So you have this balance of subatomic particles that looks very much like a star. Very much. How the metallic hydrogen, that's a different material. According to my other research, protons in particular, because see, a neutron is just a proton with electrons trapped basically at the poles.
Okay.
Above the, instead of it going around the radial or the equatorial belt, the electrons are trapped at a set distance via the attraction cone, you could say, or the polar attraction zone. They're trapped up there, which balances it out to neutral. And if you'll notice, you have neutron-containing atoms that are photovoltaic. You know, when you have an imbalance in the charges, you'll end up with photovoltaic materials. And typically, that's a neutron that its butt end or its polar end is facing outwards away from the nuclei. So.
Okay.
And so, in answer to your question, protons and neutrons appear to be constructs similar to a star, where the majority construct seems to be metallic hydrogen, but it does have an iron core. It would have an iron core, I should say. It'll have an iron core. Is it necessarily the same dark iron that we're talking about here? Electrons and what they consist of appears to be dark iron, and I guess your question directly is, are protons and neutrons dark iron too? The structure appears to be that of a star.
Okay.
For protons and neutrons. And what you end up with, of course, is, let's see, yeah, you could have a small bit of dark iron in the core.
And if you have metallic hydrogen, are those also made of electrons and protons?
Yeah, well, that's dark. That's like dark hydrogen, you could say.
Ah.
Yeah, dark matter, dark hydrogen, metallic hydrogen that's been compressed, hydrogen that has been compressed into a subspatial layer.
I guess my ultimate question is, do these subatomic particles beneath the subatomic particles also made of iron? And at what point does this recursive loop of hypercompressed iron making more iron end?
It doesn't end. It's a fractal pattern that goes up and a fractal pattern that goes down. I don't see an end. There might be.
Is our universe made of iron?
Well, it's made of it's made of iron
Just
charged
iron in
particles.
different states?
Well, hydrogen in different states. Look at the fact that we have hydrogen that can be converted in fusion reaction systems that build hydrogen or fuse hydrogen into larger elements. Iron in particular looks unique to me because it appears to be the only one that can, when compressed, form the flux lattice on the outer the outer orbitals to exceed the shearing forces of a black hole. Your magnetic field can be continually strengthened.
It can remain composed in a black hole.
Yeah, well, if it's compressed unilaterally, like or uniformly like this, and you got to consider that's a.
Then you need like a uniform iron sphere.
No, you need a noodle.
Noodle.
Yeah, it's a noodle. It's like a continuous
string
of iron that is fed down and crushed further and further and further and further down. You have different layers of compression and eventually end up with these essentially droplets or spraylets that spray out into, spin out. They spin out. No, you get a spray. Now, we see the spray. I suppose I can do that in a different color. We see a spray of gamma coming out from this crushing reaction, going outward. So we have gamma coming out. And we also have a secondary spray, which is denoted by these radial arms here and here, where the dark iron that is crushed down by the noodler, his name, it's the noodler. Noodler core. So this takes the iron and noodles it and then spins it out. Now right here, when it forms that radial spray, you get two distinct jets that travel away from that transverse binding. So at some point in here, or I should say at the point of near highest mass in here, when you have a crushing lattice, when it reaches this point right here, in that zone right there, you end up with your radial spray or radial arm patterns coming out of there. And then of course, that material, which you can see here in the diagram, is then added to the dark matter belt, which is comprised of dark iron and, well, other massive subspatial materials. And this doesn't have to be just a single layer of dark iron. Like you asked about the multi, I guess, scale. You know, does the scale go down as far as it goes up? In other words,
is our universe recursively made of iron, made of different states of iron particles?
Well, different states of compression, different states of relative compression. That's the other thing too. This is all relative. Like what we see here, the materials I'm made of, this pattern repeats itself from the hydrogen layer all the way up from what I've been able to verify to the iron layer, at least all the way across that. And if those two materials can exist at subspatial layers, I should go like this, subspatial layers, then everything in between and beyond, forward and backward, that can exist because of those two elements will exist here and there, or in those places. So essentially, you would have, if you saw my, I think it's the electrosymmetry video, I had a little graph over here that explained that because of dark iron can exist on any of the layers, and also.
Yeah, I've heard of the subatomic theory where there are just smaller universes if you go deep enough.
The math supports a repeating fractal patterned universe
and
all the way down.
And consequently, if you somehow got big enough, then you would enter it. Then you would be in some other reality.
True, or if you got small enough, you would enter another reality as well. And you know, that's definitely what we're talking about here. The monopolaric core, which you know, we can draw as red, I guess, but you know, the center of an electron is hollow, and then everything, I guess you could say all the south faces in and all the north faces out. If you wanted to break it down into just a purely a polaric base, you know. And you asked about neutral.
Yeah.
Today's video, I wanted to focus also on the structure of a photon there, and it also has a core that is hollow.
So neutral particles are just that, neutralized particles.
Well, they're neutral. It's a balance of the charges.
Yeah.
You know, in the zones, as I've drawn the photon here, a photon is just a rapidly spinning electron that these electrostrands, you know, we talked about that in electrosymmetry. These are, you know, essentially strands, you know, electrostrands. These strands, they're all bound together with force that's very similar to magnetic force, and the material itself looks like tiny balls of magnetic material. And according to what I can find, it looks like it's dark iron. So you take this electron, which is made up, it's like this fuzzy little thing that's floating around in space, and you spin it really fast. Well, through a reaction, we spin it, and then it flattens out, and these arms, or the hairs and the strands themselves, lay out across the spin. So like this one right here, of course, is but it also flips end over end, which if you've seen some of my videos, as a photon travels through, there is essentially a medium not like water, but close to it. That would be like a coin. So we have this material that it's traveling through that has like the same consistency as water. Like if you took a coin, go to any swimming pool and take just a bunch of different size coins, a bunch of different widths, a bunch of different weights, and just toss them into the water. And watch as they travel through the water. Not only do they flip over end, but they also travel in a sine wave pattern all the way to the bottom. And that's how photons travel through space. Empty space. And that's the other thing too. We're talking about a particle of light, which we know.
Yeah, it's consistent with light wavelengths and how they travel in a wave.
Yes, it is. It's exactly that. And their penetrating capabilities. Like, for example, gamma photons can penetrate normal matter. You know, it can penetrate 50 inches of silicon. Gamma photon, poof, 6 inches of lead. Poof. You know, it has a possibility of making it through. A gamma photon is similar to a neutrino in the fact that, like, a neutrino has a good possibility of traveling all the way across the width of the universe and not hitting anything. Gamma photons are a little less tight in their wavelength and their interaction with matter, in the sense that they can pass through normal matter, like I said, up to about 50 inches of silicon. But 50 inches of silicon, I mean, you can't pass through 50 inches of silicon. That's like really hard to do.
Yeah.
So it's about wavelength.
What can block a gamma particle?
And it's based upon the density and the mass of the material. You know, you got like
so what would work best, like
lead,
uranium?
Oh yeah, uranium would work. Of course, it emits radiation as well. So you want to
uranium.
Well, yeah, even depleted uranium. So anything radioactive, anything that has a half-life has some radiation. You know, they say the most stable material in the universe is a proton. It's like 10 to the 38th years. That's a while. And
yeah, I'd forgotten that depleted uranium was still toxic. It was still radioactive.
Oh yes, it is quite so. But you know, let's step away from that. Step back to the photon. So do you have any questions about how photon is structured and how the charge works?
Not really.
Do you see how that works? Basically, you have an exposed positive core.
Yeah.
You have a mount of the core, which in this case we can just draw that as.
So do light particles kind of work like gas molecules in a sense when they strike a surface, a reflective surface?
Well, I would say light particles act like a coin that's rapidly spinning.
Okay.
And if that coin strikes a surface, it bounces off that surface depending on its planar angle incidence.
Actually, how would reflections work exactly?
Materials are of same charge and they bounce off each other. Just a repulsion. You have mass versus mass, action reaction, Newton's laws.
That's what repulses it repulses the photon.
Well, you get kinetic potential and reflection and absorption and those kind of things.
Okay.
Okay, so in this case we have a semi-exposed monopolaric material that has some of the positive core exposed, so it essentially has a core of a half charge exposed on either side of the disk. You have essentially a quarter charge negative across these angled spun strands, as we're calling them, electrostrands, and overall charge across the particle is neutral. So does that mean that as the rapidly spinning photon encounters normal matter, you must understand this scale is much smaller, you know, like the difference between a proton and an electron is what, 1,830 times?
Yeah.
1,830, you know, some odd. There's a bunch of numbers. That number changes every year. They get a little bit more exact. But that number right there becomes a scale number. You can now say, okay, well, because of that, now the electron we have approximate. We know the mass of an electron based upon that. You know, it's a scale size. Its mass is almost relative to scale when you talk about subatomic particles, because they're all made of similar materials. As we're discovering, dark iron and dark metallic hydrogen, essentially. Those two materials are definitely something that I can see in my own research as materials that exist on a subspatial layer. I can't verify pretty much anything else, but I can speculate that because we can have dark metallic hydrogen because of its transverse binding nature, and also dark metallic hydrogen and dark iron. Now, you think about those two materials. Okay, those two materials. Why those two materials? Why not all the rest of the materials? Why not all the other elements? And once again, we come back to flux lines per nanometer. So we have magnetic flux lines, which I will now draw here. Magnetic flux lines coming from a material. You got all these little flux lines come out from a material. And that flux lines, when space compresses that material, these flux lines per nanometer, so we have flux lines per nanometer, exceed the shearing force of a black hole. So we have several things that occur here. We have a shearing force and we have a compression force. And when the compression force crushes down iron or metallic hydrogen below a certain layer, both of those materials have magnetic fields. Now, iron has 50 times less the magnetic field potential of metallic hydrogen, 50 times. So does that mean metallic hydrogen could exist in a layer 50 times deeper than dark iron? Yes. So 50 orders of magnitude. Is it orders of magnitude? No. Times. So 50 times is the difference between metallic hydrogen and iron. But both of them generate a magnetic field. So if you looked at the magnetic field on iron, Fe, and you looked at the one between metallic hydrogen, we're just going to do just hydrogen, and then we're going to do, I guess M would be fine, Fe1, and you take either one of those and compress them down to where your flux lines per nanometer was greater than the shearing force of, which I guess, if you really wanted to, you could do a black hole. But, it's near infinity, so infinity 1 over time 1 x, y. When your flux lines per nanometer exceed that of, or greater than, infinity of the first, infinity of the first minus reality, or relativity 1, over time 1, x, y, z, or x1, z1, y1, z1, and that equals interest into subspace. Okay, anyway, so like I said, your flux lines on metallic hydrogen, or I was saying, are 50 times that. So you have a 50 times more powerful field, magnetic field, around metallic hydrogen than you do iron. So now how do you get? Well, I guess that means that this belt here is made up of dark matter. Like I said here, I wasn't sure of all the types of dark matter that were going to be there, but essentially metallic hydrogen and that makes sense, doesn't it? It makes perfect sense. Metallic hydrogen is 50 times more powerful magnetic field than iron.
Yeah.
Because you don't have the nucleus effect.
Oh.
Where you have the nucleus and you have that huge space, and then you have the electron orbitals way out here. You have a single metallic hydrogen, or a single piece, single nuclei, single proton with a single electron going around it, and the space there, you can make it that much more compact.
Speaking of which, it reminds me of neutron stars, which apparently have a different atomic structure. They have the nuclei piled on top of each other.
Sure. That's theory, though. I've never seen an example here on Earth of any type of that's all theory. That's all math. They're speculating with neutron stars. Now, their speculation might be good. Their computer models might work, but computer models can be flawed. And one little tiny mistake in the beginning of a large chain of mathematical equations can screw everything up.
it's like you're a degree of angle off, and
Oh yeah. I mean, okay, yeah, exactly. You're like 1 degree off, or a billionth of a degree off, and you're talking about calculations that go out a billion places. That can mean you're in a totally different section of science or of the universe. I mean, honestly. So yeah, it takes nanometers of flux lines per nanometer versus the shearing force over time and space of a black hole, or of time and space, essentially. And when you can exceed that shearing force that is generated here inside the noodler core, then you can have dark matter. And that's where dark matter comes from. And that right there, interestingly enough, this week, this is what's cool. I love doing this stuff. It's fringe physics, right? So cool. I just drew this. Okay? Like what? The day after I made the other video, so it's been like a week.
Oh yeah,
It's been like less than a week. Interestingly enough, the most recent observations of scientists of our galactic core match my calculations. They match it perfectly. They show that the star, as it's sucked in, you know, it's pulled apart and its mass comes down in there like this and spirals in. That's what we're observing that right now. So we see that, we know what it's doing, and then of course it's radially sprayed out to that, and it's added to the dark matter ring. The ring is there, everything's there. Everything that I've been talking about here, you can look it up on like pbs.com. They've got a thing on, well, at least on black holes, that I really explain the dark matter and the dark energy and monopolar cord, electrons or photon structure or anything like that. You know, me, I'm here to help mankind understand this stuff. And thank you so much for joining me today. If you have any questions or comments, please put them down below. There will be other videos, of course. We're going to move into other subjects. We've had some questions, we've had some requests, so we're definitely going to be moving more into those since we have time. And you know, get a good look at the board. Let me stand back here for a moment. This will be the last time this board is recorded, so there you go. You know, screenshot it or whatever, and good luck with your research. Good luck with your scientific pursuit of the universe and what it contains. There's so many more mysteries, but it's like anything else. You know, once you figure it out, you can use these things, and where you apply them, where you take them, can lead mankind into a brand new era of science. So good luck, YouTuber scientists. And keep going, man. Keep looking for the answers, because eventually you're going to find some really cool stuff. Talk to you later.